Hello! Welcome to lesson 21 of Environmental Management IGCSE. Today we're getting stormy. It's all about tropical cyclones. Look at that beauty right there. Pretty fantastic. Now, what we're going to do today is we're going to have a look at what makes a tropical cyclone happen and how we measure it as well. I like to think of a tropical cyclone as a fine cake. It's got many ingredients that need to be just perfect, or else, well, you don't get a cake, you just get a mess, I guess. And yeah, our tropical cyclone is like that. We've got an ingredients list that we need to understand to be able to understand what a tropical cyclone is and yeah, how it works. So let's have a look at that ingredient list. The first thing we need is warm water. Oh yes. Now they're called tropical cyclones for a reason. And in fact, they're not always called tropical cyclones. Tropical storms in general. But tropical storms, cyclones, they change their name depending on where they are in the world, right? So if they're off the coast of the Americas, there are hurricanes. So think of things like Hurricane Irma, Hurricane Katrina, these famous hurricanes. Either side of the Americas, that's what we call them. If they're sort of hanging out in the Indian Ocean, we call them cyclones instead, and that's the term that we'll use a lot here, and that's the term that the syllabus, the exam board, tend to use, cyclones. If you go off the coast of East Asia, though, sort of south of Japan or whatever, then we call them typhoons instead. And the Australians, because they've got their own special way of doing things, they tend to call them willy willies. I mean, cyclones. We'll go with cyclones, right? So it's the same phenomena. It's just, or phenomenon, but it's depending on where they are, is a different name for them, right? So it's kind of like magma lava. Yeah, it's essentially the same thing, but we call it lava when it's streaming down a volcano. We call it magma when it's under the ground. So here we've got this strip of land in between the two tropics. You can see there on our map the Tropic of Cancer in the north and the Tropic of Capricorn in the south. Right between the two, equidistant to the two, is the equator. It's the middle of the world. So these are our lines of latitude. Tropic of Cancer runs... Cancer? That sounded kind of spacey. The Tropic of Cancer runs at about 23 degrees north, whereas the Tropic of Cancer is about 23 degrees south. You see there, they're equally spaced, with the equator running at 0 degrees. Now we call this area between the two tropics the tropics, or we call them the tropical zone, right? And the tropical zone is where we're going to find, generally speaking, the warmest temperatures on Earth. If we think about land, that's where we get the rainforests. You've got the Amazon there in South America, you've got the Congo in Africa, and then you've got the various Asian rainforests across Southeast Asia. And the water is warm too, and that's the important thing here. It's got to be warm water. You're not going to get a tropical cyclone occurring off the coast of Britain. The water's just too cold. But that's not the only thing we need. You don't just need warm water. If that was it, it would be a very simple cake, very simple ingredient list, wouldn't it? And we'd just have tropical storms all the time in the tropics. No, there's plenty more things that you need to add to it. So, step one, first ingredient, warm water. We're going to find that in the tropics. We also need a lot of wind, right? Now we're going to pause in our ingredient list for a second just to think about what a tropical storm is, what it looks like, what it feels like. And that's going to help us discover what comes next for our ingredients. So we're going to imagine here that we're somewhere in the tropics, right? I don't know, Brazil or Jamaica or Philippines, somewhere like that. And it's a nice sunny day. Oh, it's usually sunny in the tropics. It's nice and warm, clear blue skies. But in the distance, we start to see things change. We're going to see, at first, white, wispy clouds. But they're soon going to come closer, and they're going to grow, and they're going to be, well, quite scary. So as the hurricane approaches, or the cyclone, or, the typhoon, whatever, as it approaches, we're going to notice the temperature starting to drop. as the pressure drops around us in the atmosphere. Winds are going to start off gentle, but they're going to start to get a little bit more aggressive as it gets closer. The clouds are beginning to form and showers start to develop. So we've gone from clear blue sky to fluffy white clouds, a little bit chilly, bit of rain. But then as it gets closer, as it nears us, as it's about 30 to 50 kilometers away from us, we start to get the big drop in pressure. Starts to get proper cold. The winds, they whip up to 100 kilometers per hour. We look up in the sky, and if we haven't already run in for shelter, we look up and we see these great cumulonimbus clouds. These are huge clouds, the biggest clouds that we get in our troposphere, which is our area of the atmosphere. They're absolutely huge. They're shaped like anvils. The tops of them are so high up in the atmosphere that they are frozen. They're ice crystals right up there. Whereas the bottoms of them are like many of the clouds that we're used to. They are liquid, droplets of water hanging onto dust. And the whole thing makes this huge sort of funnel-like anvil shape. Big at the top, slightly bigger at the bottom, a bit narrower in the middle. And what's happening there is we're getting convection currents. The same convection currents that we keep mentioning in this course, right? We've mentioned it with magma and water and all sorts. But we're getting these convection currents working. We've got warm moisture rising up off that warm sea, right? We said the sea had to be warm. And that's lifting up into the air. And as it moves upwards, it's being displaced by cold air, which is causing this circular motion. So what we're watching is the clouds coming towards us and they're spinning. Oh yes. Now, we're going to get hit by the full force of this tropical storm. It's going to hit with clouds. Thunder's going to start to clap. We might even get a bit of jolly lightning in there. And the rain is going to be torrential. As it comes towards land, it's going to start bringing the ocean with it. So not only is it raining down from above, but it's surging the ocean ahead of it, which means that we get the ocean appearing on land. Floods galore. It's pretty scary. But all of a sudden, we're in the middle of all this chaos. All of a sudden, everything changes again. The winds drop. The temperature rises up again. Ooh, nice. We can see the sun in the sky. The rain stops. Now that's because we're in the center of the storm, the center of the cyclone. This is called the eye of the storm, or the eye of the hurricane, or the eye of the typhoon. It's the eye. This is the central bit. And if we go back to our picture at the start there, you'll get a better idea. Here we can see the eye. This picture is taken from satellites in space, and we can see that place of calm. It's like the storm is swirling around this central point. So if we were stood in there briefly before the other side of the storm hits us, it would be quite nice, be quite chilled, right? But of course, no, it races on past. We get hit again. Massive winds, loads of rain, thunder, lightning, crackling, storm surges as the ocean gets pushed up onto shore. But if we're still alive, if we're still on our feet, we would notice that storm will pass us by. And as if by magic, as if it had never happened, the sky will open up into bright blue again, the clouds will disappear, the temperature rises. Now we look around at us at the devastation that's been left. Everything's kind of soggy and broken. But, climatically it's as if it was never there. It's gone on by. We're in the sunshine again. So what are these other ingredients that we need then? It's obviously not just warm water, right? Well, we need to talk about that spin. Okay, why is the air moving in the first place? How do we get that circular motion that forms that eye and that sort of funnel as it moves around? Well, one of those ingredients is called the Coriolis effect. The Coriolis effect is a very complex atmospheric thing, but I like to think of it as, I like to start by thinking about it as a pizza. You've got a nice big round pizza, not one of those weird square ones. That doesn't work with the metaphor. So go with a standard round pizza. And on that pizza, we've got two ingredients. We're going to put here something blue, a bit of blue cheese, and here something pink, a shrimp. It's not a good pizza, okay? It's a blue cheese and shrimp pizza, and there's only one piece of each of them. But it's going to help us understand the Coriolis force. Now we're going to start spinning this pizza around like an amazing Italian chef, right? We're going to start spinning that pizza round and round and round. And as it spins, we can see, well, for a start, there's a weird grey box bobbing underneath. That's fun. But we can see that the blue and the pink, our blue cheese and our shrimp, are moving around. And well, they're moving completely in place with each other. I can spin it faster and faster and faster and faster, and no matter how fast I spin it, the blue cheese is still in line with the shrimp. So what's that telling us? I mean, why am I spinning a pizza? I mean, other than having a weird hobby, I'm trying to show you that we've got the two shapes, the two colours there, the two blobs. They're moving in tandem with each other, which tells us something important. That shrimp is going to be travelling less of a distance than that blue cheese, right? Because the circle, that inner circle, that pink circle that we see, that's a smaller circle than the outer circle, which is blue, or the blue bit is on. So if that's the case, then why are they not sort of coming out of sync? Why is the pink bit not moving fast around than the blue bit, and we end up with the blue bit over here and the pink bit over there? Well, we're kind of getting to the Coriolis effect here. If something travels a greater distance in a shorter amount of time, then it must be going faster, right? So that blue piece of blue cheese, say, is moving faster than the shrimp. Because otherwise, if it wasn't, they wouldn't be able to keep up with each other. Okay. Now, that's on a 2D surface. Yeah, that doesn't really tell us much, I suppose. But now let's turn that into a 3D shape. Something roughly spherical, like our planet, right? And then let's say that pink dot there is Greenland, up there near the poles. And that blue bit there, well, that's the equator, that's Brazil, okay? As our planet spins around its axis, that means that we're getting the same effect as on that pizza, right? We're getting Greenland moving slower than Brazil, because Brazil is on the outside of that circle. So Brazil must be moving faster than Greenland. I mean, yeah. I mean, I haven't seen Greenland being brilliant at football recently, but Brazil's pretty good, right? They can move fast. I'm not sure that's my point. But the thing to remember here is the Earth is spinning faster at the equator and slower at the poles. This explains, or goes some way to explain, why we have circulation of air movement around our planet, right? Why is the gas of our planet just not still? Why is it always blowing and winding? Well, the Coriolis effect is playing a part there. It's causing those winds to happen. So we need the Coriolis effect to be in force in order to create enough wind, enough spin, to get our tropical storm off the ground. So that's ingredient number 2. Let's talk about the wind a bit more, though. So we've got these convection currents. Yeah, we've talked about convection currents. This is where hot things rise, they're displaced by cooler things, which fall. This is what's happening in the atmosphere, but it's happening in what these great areas called cells. These cells, these areas of our planet or our atmosphere above the planet, they're individually making convection currents. To put it simply, at the equator, where we're spinning faster, everything's warmer. Yeah, it's getting more sunlight for longer each day. Everything's warmer, the climate is warmer, the air is warmer. So we're getting air rising there. But at the poles, a further latitude north or south, well, we're getting the opposite. It's very cold, the air is very cool, so the hot air rises at the equator, it sort of shoots through the air towards the poles, it gets displaced by cold air coming from the poles, and we get these big circular motions. And they're pretty reliable, these circular motions. We call them the trade winds, or the prevailing winds. These bars, these lines of latitude across our planet, each one of them has a different prevailing wind direction. Prevailing just means the almost always direction, to put it in a slightly silly way. So it's the way the wind 9 times out of 10 will be blowing, the direction it's blowing. So if we're in Britain, yeah, like I am right now, I'm in this band here. Let me zoom in. Here we go. So I'm in this band here, right? Here's Great Britain, here's most of Europe, there's North Africa. They're all in the same big area with this huge big cell of convection currents above us. Now, the direction of wind travel in this area, we call them the westerlies. They come from the southwest and they leave by the northeast. So if I'm down here in Cornwall, you'll notice if you ever, if you hang around in Cornwall, Cornwall's pretty windy, right? I mean, that's partly because there's nothing to shield it, because the wind's coming straight off the ocean. But that's the problem. The wind's coming straight off the ocean from the southwest, and Cornwall is the southwesterly point of Britain. Whereas if I'm over in York, it's generally a bit calmer because the wind is coming across the land, so it's sort of buffered by trees and houses and hills and mountains and all that kind of stuff. So York is relatively less windy than Cornwall is, or Wales, say. So we can, on any given day, you can pretty much guess which way the wind is blowing. It's blowing from the southeast to the northwest, but this isn't the same everywhere, right? It's, completely the opposite. If we go down a band to the Sahara here, what we've got here is our northeasterly trade winds. So they're coming from the northeast and they're leaving by the southwest. That's the opposite direction that we're getting in Europe. Now, they're called the trade winds, or they are commonly called the trade winds, especially these two bands here, the northeasterly and the southeasterlies, because back in the day when people were sailing from Europe to the Americas, say, across the Atlantic, they were using sail, and it's pretty difficult to sail from Britain to Canada in a straight line with sails, because the wind's always blowing in the opposite direction. You can try it, it's going to push you back home. So how do you get to America? Well, if you want to get there, you have to sail down past Spain here, down the coast of North Africa, until you get into an area of northeasterly trades, and then whoosh, you can catch the sails and boom, you get over to the Caribbean, and then you can sort of scoot up the coast of Canada if that's where you want to go. But if you want to get home again, you're not going to be able to go the same way because the wind's blowing against you. So you head up north, right? You sail up to North America, Canada, and then whoosh, this wind is in your sails and you can get back to Europe. So, sailors back then, it was this great big circular motion they had to make in order to get from A to B, if A is Britain and B is America. So that's why they got the trade winds, because it's the traders that are using their ships. So let's keep adding these ingredients then. We've got to have warm water. We've got to have wind movements. We're looking at the Coriolis effect, the Coriolis force. We're looking at convection currents. We're looking at the trade winds. All of this is combining to give us movement of air in our atmosphere, which is going to help get this thing spinning. But there are more ingredients that we need too. So we need air to be warm. This is going to happen in the warmest months, right? The air needs to be above 27 degrees centigrade in order to cause a tropical storm. On a cool, cold day with lots of shadow, not going to happen. So we need warm air. That's going to be giving us maximum evaporation off of that warm ocean, which means we're going to get the maximum amount of convection currents running. We also need that water to be deep, at least 50 meters deep. You're not going to form, if you're planning on it, you're not going to be able to form a tropical storm in your bath, right? You could get the water hot, you could get the air hot. You could even do something weird with a fan and try and get the spin going, but it's not going to be deep enough to get that pop in. So, the water has to be deep. We also need, again, the water to be warm. It says here the sea must be at its warmest during late summer. Now that's going to be different depending on which hemisphere you're in, of course. So the southern hemisphere, those willies off the coast of Australia, they're going to be happening at a different time than the hurricanes in North America because their summers are inverted. We then need the circulatory motion of the air. This will always be anti-clockwise in the northern hemisphere, so spinning that way, whereas in the southern hemisphere it will always be clockwise. It's one of those funky things that happens when you get from one hemisphere to the other. And this is going to be encouraged by Coriolis force. That's going to give us that initial spin. And then finally, when all that is ready, we've got the warm air, we've got the deep warm water, we've got the Coriolis force working, then we need a little bit of spin. Something to get it going. Like you've got the top ready, that one of those little toy tops. You've got that ready on your desk, and all it's waiting for is for someone to take it and go, whoop, just get it going. Well, that's going to be a small change in wind speed and a direction with increasing altitude. This is wind shear, so we need a quick movement of altitude. So the wind suddenly goes, whoop, Now that can happen for all loads of different reasons, but that's what gets the circulation starting. That quick change in wind speed or height, and boom, the whole thing's running. And once it's going, it will then keep going as long as it's fed by those same ingredients, right? So that it will only survive. And I know I'm talking about like a living thing here. I'm personifying a storm, people, but it will only keep running if it's over those same conditions. If it runs into somewhere cold, it will peter out of energy and stop. If the water disappears from under it or stops being so deep, it will peter out and die. If for some reason the wind stops blowing, then it's gonna stop and die, right? And so these things are really dangerous at sea, but as soon as they hit land, they lose all of these ingredients. Land is generally cooler than sea, or at least the surface is, so that's no good. Certainly not deep water, so that's no good. And so as they hit land, they sort of falter, they get quieter, and they die. Now, this means that if you're well inland, let's say you're living in Kansas in the USA or something, you're never going to have to worry about a tropical storm. But if you're living on a Caribbean island, or in the Philippines, which is this huge archipelago, then those storms can come raging in off the water, and yes, they might slow down slightly as they hit your little bit of land, but it's not enough to stop them, and they'll just keep on ricocheting and bouncing around and head off in a different direction. So the people most at risk of these are people in coastal areas and island areas. That's where you're going to get hit by a tropical storm. If you're well inland, any tropical storm would die long before it gets to you. So, how do we measure these things? Now, tropical cyclones, they're pretty scary things, but we do have a way of categorizing them, and we put them into 5 distinct categories based on mainly their wind speed, but also other factors too. And we've got a nice little breakdown here of what that looks like. Now, the way that these are measured, this scale is called the Saffir-Simpson scale, the Saffir-Simpson. And I assume made by doctors called Saffir and Simpson, or maybe one doctor with a double-barreled name. I'm not sure. I should have looked it up. I didn't. I'm sorry. But these categories, they go from 1 to 5. 1 is the smallest, and 5 is the biggest. And this little table here shows us what's going on. So a category 1 tropical cyclone has a wind speed of somewhere between 74 and 95 kilometers or miles per hour. Sorry, we're going to work in not imperial here. So pretty high wind speeds. You're going to notice it, right? This is wind speeds that are quicker than the speed of a cheetah. I mean, it's a strange thing to compare it to because they're very different things. But cheetahs are fast, and this wind is faster. Just go with that, right? It's not going to damage your property much if you've got maybe a tent up, or maybe a caravan that isn't anchored down. It might get wobbled or knocked over or something. Your trampoline may fly across the garden or something. So it's not too devastating. If you're living right next to the coast, you will experience a storm surge of between 4 and 5 feet, which is roughly 1.5 meters ish, something like that. That means a storm surge is where the water is pushed up by the storm out of the ocean onto the land. So you would only notice that if you were relatively near the shore, because 5 feet of it's like a high tide in many ways, right? But as we go up the categories, it gets worse and worse, stronger and stronger. You can tell this is an American source, can't you? Because the second one talks about a pitcher's fastball. Now, I have no concept of how fast a pitcher's fastball is. Well, I do now. It's about category 2 in terms of cyclones, right? But the wind speed's 96 to 110 miles per hour, 6 to 8 feet of storm surge, and it gets worse and worse and worse. We'll see that we've got the serving speed of many professional tennis players. That's category 3. And then faster than the world's fastest roller coaster. I mean, I don't know. I have no idea how fast the world's fastest roller coaster is. Well, I do. It's at least 130 miles per hour, I guess, or just under that. Really fast. Fast roller coaster, faster wind. And then finally, we hit the maximum one. This is going at the same speed as a high-speed train. I mean, I guess a high-speed train going really fast, right? Not like a slow one on a rest or anything, on a break. But this, the winds are really, really strong, really powerful. By this point, we are smashing down houses. We're uprooting and smashing down trees. That's complete catastrophe, Category 5. To give you an idea, probably about Category 3, that's when your roof tiles are going to start flying off and landing in the garden. Category 4 is where your roof is probably going to start lifting off completely. And Category 5 is where your roof has gone, but so is the rest of your house. It's pretty devastating. That Category 5 there has a 19-foot storm surge. So even if you're not particularly close to the coast, 19 feet of extra water coming up off the coast, you're gonna notice it. And if you are living right on the coast, you are underwater at that point. You are deep underwater. It's not good. So these things can be pretty devastating. But once again, we will talk about the devastating nature of these. Is it next week? No, not next week. The week after next. I'm sort of building up with all our different disasters and hazards. So yeah, this is how they work. But we'll talk in the future about the specific damage they do and ways to deal with it and manage it, right? In terms of trying to prevent tropical storms, it's not really a thing. Yeah, those ingredients are all natural ingredients. Yeah, warm water, deep water, warm air, Coriolis force. There's nothing humans can do to prevent these things. But what we can try and do is roll with the punches when they come. So we'll talk about that again in a future lesson. But there you are. That's tropical storms. They're quite exciting, right? Quite dramatic. I hope you enjoyed that. And I'll see you next week where we're going to be talking about floods and droughts. Two sides of a kind of coin, I suppose. So I look forward to seeing you then. Bye.